So let's start by sketching this region. Look at the expression that we have. This looks pretty awful. Y equals the square root of something, but usually, at least at beginning simpler questions in a Calculus 2 course such as this one, the whole idea is to square both sides. So when I square both sides, I'll get y squared, 4 minus 2x squared. If I move the x to the left, that's 2x squared plus y squared equals 4. Divide both sides by 4. So that is a 4 actually. That is pretty clearly, if you remember pre-calculus, an ellipse with minor axis along x at root 2 and then negative root 2, and then major axis along y at the square root of 4, right? So 2 and negative 2. So this is pretty much the shape of this guy. Now if I'm being formal, if I'm being careful, when I started with this, y equaled the square root of something. So y needs to be positive. Even though I got the shape of an ellipse, all that shows is that my equation, my graph, my shape is inside. It's part of the ellipse, right? Not in the interior, but on it, right? It's part of it. And because y needs to be positive, in fact, I only have this half. So formally, this bottom here is not part of my region, only this is. But it doesn't matter because we're also told in the next step that we are in the first quadrant. So we are here. In any case, this is the only part of the ellipse we are considering anyway. So this is my region right there. Just to make sure, this is a root 2. Okay, so here's a root 2, and this is a 2. So we're now trying to find the volume of the solid generated when the region is rotated around the y-axis. So we're rotating that around the y-axis like this. We could do this in many different ways. I feel like the disks method maybe would be easier. But the idea here is to use the shells method. So if you solve this by using the disks method or another slicing method, you'd be incorrect. That is not what you were asked to do. So we need to use the shells method. So be careful. Watch out for what's going on, what you're being asked. So let's go ahead and use the shells method. What is going on with the shells method, right? Remember what we're doing. We're looking at the solid. So the solid that we get is something that looks like this. Once the rotation happens, we're rotating this guy around like that. So we're getting something that looks like that. And we're splitting this into separate shells. So like there's this shell right there that goes around. That's one volume. And then there's this higher shell. Right? So all of those are shells that were sort of small and slowly contributing to form the volume of the whole thing. Each of those shells are going to form the volume of the entire solid. So what we do is we integrate. It could be dy or dx. In this case, it's going to be dx. But we're integrate the area or the volume of each shell. So how do you find the volume of one shell? Let me erase this. Do it again without so many polluted shells there. So I'll draw only one shell. And I think this is a good idea, a good explanation. So this is my one shell that I'll calculate the volume of. It's very thin. Whenever I'm dealing with something very, very thin, I'm calling this thickness, right? I'm calling it dx. And what I do with this shell, so imagine this is like a cup, right? A cylinder without a bottom. This doesn't have a bottom. Or pipe or something like that. It's hollow in the middle. And we can cut it out, cut it in here in one of the sides and unfold if it were a sheet of paper or something. And unfolded, that turns into, not exactly, but approximately, which is fine for us. Since we're dealing with infinitesimal volume. Turns into this sort of thick sheet of solid. So we have to find the volume of each of those sheets. So we have this thickness right there. This thickness is this little thickness here, right, of the cup. So this is what we call dx. It's a very, very thin, infinitesimally thin. The height, right, is this height. So if you go back to the graph, it is this height. So it is the y coordinate. So this is y. So maybe this is y. And then the length is the most complicated thing to understand. This is the circumference here. So maybe if I highlight, this length is this length. So it's the length or the circumference of a circle, right? That's 2 pi r. In this case, the r, the radius, is this distance from the center to the shell. So it is x. So it's 2 pi x. Now I have the 3 dimensions of the shell of this solid that we're integrating the volume of. So this is 2 pi x, so base times y times dx. Okay, so multiplying these 3 things, we get that. Take a second to see it. And now all I need to do is integrate it. So as soon as I understand what needs to be done, I just integrate. I think this drawing is pretty important. Doesn't cost much to add it. And now all I need to pay attention to is to what y is and integrate it. Oh, there's one more thing actually. Maybe you've already noticed it. I forgot to calculate the limits of integration. Because this is an integral dx, I will have one shell for each x value. For each x value, I have a different shell, Right? So I'm integrating in terms of x. And x is going to vary from 0 to root 2. This is my integral. Right? Look at how x changes right here. X goes from 0 to root 2. So that is these are my limits of integration. I just have to integrate that. So let me use my time a little bit more cleverly than I did last time. I'll split this up into 2 parts. So I'll do that. So I have some squared function, some quadratic function inside of a square root. So it may be a good idea to use some u substitution and write u equal to 4 minus 2x squared, just so it becomes the square root of u. And then du is minus 4x dx. So minus 1/4 du is x dx. And conveniently there's an x dx that shows up in there. So I'll replace that with a minus 1/4 du. So my integral is actually, so minus 1/4 I'll write out. Du. This 2 pi stays, so put it here with the 1/4. And then the square root of something is the square root of u. I'll calculate the limits of integration. I'll recalculate them, right? So this is part of the u sub. When x equal to 0, u equal to 4 minus 2 times 0 squared, so 4. when x equal to root 2, right, the top limit, then u equals to 4 minus 2 root 2 squared. So that is 4 minus 2 times 2, 4. So 0. Top limit is 0. Now how cool this is. We're calculating a volume, so the answer should be positive, but we have a negative here in front of it. But it's fine because now the limits of integration are in decreasing order. The 4 and the 0, right? The 4 is bigger and is at the bottom. So once we do the calculation, either we switch the order and fix the sign in front, or we just do it that way, and the signs are going to work out by themselves, and we're going to get a positive answer. So finding the antiderivative of u, square root of u. Square root of u is the same as u to the 1/2. So I use the reverse power rule. It is adding 1 to the power. 1/2 plus 1 is 3/2. And then divide by 3/2. That evaluated from 4 to 0. Fixing that, I miswrote that. That was a 4. I can even simplify that to write a minus pi over 2 instead, just to avoid future mistakes. This 3/2 that's dividing can turn into a 2/3, right? Dividing by a fraction is the same as multiplying by its reciprocal. And then u to the 3/2, 4, 0. Haven't evaluated anything yet, just trying to make my life easy, but I will evaluate things now. So pi over 3. So I will plug in 0 into this guy. And 0 to the 3/2, that is just 0, minus 4 to the 3/2, that is the same as root 4 cubed. Right? Square root, right? Because this 2 turns into a square root. And the final answer is 2 cubed, which is 8. So the answer is 8 pi over 3. Positive because the minus signs cancel out. So this is it. This is the final question on this list. This is how you calculate the volume using the shells method. Again, I'd really appreciate a drawing on this question.